For the first question in trapezoidal rule of integration, we are asked to find for the solution to equation 5x squared minus 6x plus 2 with x sub 1 is equal to 1, x sub 2 equal to 3, and step value or h equal to 0.5. In solving this problem, we need to tabulate first the values we will be needing, which was the values of x and y. So corresponding to the values of x sub 1 and x sub 2 that has a step value of 0.5, we can say that values of x will be 1, 1.5, 2, 2.5, and 3. On the other hand, for values of y, we will now substitute the following x's we obtained to the equation, which results to 1, 4.25, 10, 18.25, and 29. After this step, we can now proceed in solving proper using the trapezoidal rule that has a formula of h over 2 times the quantity of y sub o plus y sub 4 plus 2 times the quantity of y sub 1 plus y sub 2 plus y sub 3. So substituting the corresponding values for this, we then obtain 31 as the solution for equation 5x squared minus 6x plus 2 by trapezoidal rule. Thus, the correct answer is letter C.
Moving on to the second question from the trapezoidal rule of integration. Find the solution using trapezoidal rule. We have here a set of values for x and fx. For x, we have 0.25, 0.5, 0.75, 1, and 1.5. For fx, we have 4, 2, 1.333, 1, and 0.8. We have 4 choices here. For A, we have 1.67, 520. B, we have 1.38754. C, we have 1.68325. D, we have 1.25863. So for the solution, we will integrate integrate y, which is equal to h over 2 times the quantity of initial y plus y sub 4 plus 2 times the quantity of y sub 1 plus y sub 2 plus y sub 3. So evaluating it, we will have 0.25 over 2 times the quantity of 4 plus 0.8 plus 2 times the quantity of 2 plus 1.333 plus 1. Simplifying it further, we are going to have 0.25 over 2 times the quantity of 4 plus 0.8 plus 8.666. And finally, we will have the answer of 1.68325. That is letter C.
For the third question in trapezoidal rule of integration, a function f of x is given by the table values. Approximate the area under the curve y is equals to f of x between x is equals to 2 and x is equals to 10 using trapezoidal rule with n is equals to 4 sub-intervals. The choices are A is 20, B is 80, C is 40, and D is 60. For the solution, using trapezoidal rule, the integral of y dx is equals to h over 2 times y sub 0 plus y sub 4 plus 2 times y sub 1 plus y sub 2 plus y sub 3. Substitute the values 2 divided by 2 times 7 plus negative 3 plus 2 times 11 plus 9 plus 3. 2 divided by 2 times 7 minus 3 plus 46 is equals to 80. The approximate area under the curve is 80. The correct answer is letter B.
Hi, this is Mohammad Maulad, and this is the continuation of trapezoidal rule of integration number 4. Using the trapezoidal rule with n is equals to 5 subintervals, evaluate the integral of dx all over 1 plus x squared with upper and lower limit of 1 and 0, and calculate the approximate value of pi. Round the answer to 2 decimal places. Before we proceeding on answering, first we must find the value of h. In order to get the value of h, we have a formula for it, which is h is equals to b minus a all over n. And then we simply substitute for the value of b, which is 1, and value of a, which is 0, and value of n, which is 5. And now to solve for h, we get 0.2. Now we can proceed on solving for the integral of dx all over 1 plus x squared with upper and lower limit of 1 and 0. Now using trapezoidal rule and the given they have given us here, the value in the table of values, we get integral of y dx h all over 2 times the quantity of y sub 0 plus 2 times y sub 1 plus 2 times y sub 2 plus 2 times y sub 3 plus 2 times y sub 4 plus y sub 5 until y sub 5 because the given here until 5. Now we just simply plug in the value of y's based on the table they have given us. After plugging in, we multiply them by 2 each and then we add them all up. After multiplying and adding, we get the value of 7.8374. After we get that, we multiply that to the value of h, which is 0.2, and then we divide by 2. And we get 0.78374. Now this is the value of our integral of dx all over 1 x squared, 1 plus x squared, with the upper limit of 1 and 0. Now we can solve for the value of pi by using the fundamental theorem of calculus. In order to get that, we get the integral of dx all over 1 plus x squared. We equate that to arctan x with upper and lower limit of 1 and 0. Now to just solve it, we get arctan 1 minus arctan 0, and we get pi over 4 minus 0. And then what we get is only 5 over 4. Now we solve for pi. Equate them to dx all over 1 plus x squared. We isolate pi and we get this 4 times the integral of dx all over 1 plus x squared, which we already get the value from the previous by using the table, and that is 0.78374, and then we simply plug that in and multiply by 4, and then we get the value of pi 3.13.
The first question in Rugi-Kutta fourth order method ode is to solve the ordinary differential equation 5 dy over dx plus xy squared is equals to sine x, where y of 0 is equals to 4. By Rugi-Kutta fourth order, you need to rewrite the equation as a dy over dx is equals to sine minus xy squared, where y of 0 is equals to 4, and b dy over dx is equals to 1 over 5 multiplied by sine x, where y of 0 is equals to 4, and c dy over dx is equals to 1 over 5 multiplied by sine x minus xy squared, where y of 0 is equals to 4, and d dy over dx is equals to 1 over 5 multiplied by negative cos x minus x y raised to the 5th power over 5, where y of 0 is equals to 4. So solution. We're going to write the equation 5 over dy over dx plus xy squared is equal to sine x. First, you should subtract the xy squared to the left side and to the another side so we can cancel out the xy squared in the left side. After you subtract it, you're going to multiply now by 1 over 5 in the left side and to the another side so we can cancel out the 5 and dy over dx. So we came up the answer dy over dx is equals to 1 over 5 multiplied by sine x minus xy squared, where y of 0 is equals to 4. So the correct answer in number 1 Rugi-Kutta fourth order method ode is letter C.
For problem number 2, use Rugi-Kutta method of order 4 to solve the following using step size of h equals 0.15 for x is greater than or equal to 0 and less than or equal to 1. Equation is given as dy over dx is equal to 5x squared minus y all over e raised to x plus y with y0 is equal to 1. For its solution, we need to solve first for the value of f1, f2, f3, and f4. For f1, only direct substitution will be done to the given equation using 0 as the value of x and 1 as the value of y. This results to negative 0.0551819168. Unlike in solving for f1, in solving f2, new values of x and y is needed to be solved first. For x plus h over 2 will be used, which results to 0.075. For y plus f1 over 2 will be used, which results to 0.97240904191. After this, we can finally solve for f2 using this formula. f2 is equal to hf times the quantity of x plus h over 2, comma y plus f1 over 2. Substituting the corresponding value, we obtain negative 0.04969468501 for f2. Going on in solving f3, we need to solve for new value of y using this formula. Y plus f2 over 2, which yields 0.9751526575. After this, using f3 is equal to hf times the quantity of x plus h over 2, comma y plus f2 over 2, we then obtained negative 0.049703539098 as the value of f3. Lastly, for determining the value of f4, determination of new y will also be done first. We then obtain 0.95029747902, and after substituting it to f4 is equal to hf times the quantity of x plus h, comma y plus f3 over 2, we acquire negative 0.049616079196 as the value of f4. Now that values of f1, f2, f3, and f4 are solved, we can finally use the general formula for Runge-Kutta fourth order method, which results to 0.94940126665. Therefore, the correct answer in question number 2 is letter B.
For the third question for the Runge-Kutta fourth order method ODE, given 6 dy over dx plus 10 y squared is equal to sine x comma y 0.3 is equal to 5, and using a step size of h is equal to 0.2, the value of y 0.8 using Runge-Kutta fourth order method is most nearly. So for A, we have 1.1216. For B, we have negative 4.321. For C, we have negative 1.320. And D, we have 3.1415. So for the solution, we would turn the equation 6 dy over dx plus 5y squared is equal to sine x comma y 0.3 is equal to 5. It will be written as dy over dx plus 1/6 times the quantity of sine x minus 10y squared comma y 0.3 is equal to 5. This is from the Runge-Kutta fourth order method, which is initial y plus 1 is equal to initial y plus 1 over 6 times the quantity of k sub 1 plus 2 k sub 2 plus 2 k sub 3 plus k sub 4 times h. So if using that equation, we will substitute k sub 1, which is f x is initial x comma initial y, at k sub 2 f of x initial x plus 1 half h comma y initial plus 1 half k sub 1 h. For k sub 3, we will have f of x initial plus 1 half h comma y sub I plus 1 half k sub 2 h. For k sub 4, we have f of initial x plus h comma initial y plus k sub 3 h. So you will have a value for I which is equal to 0. X sub 0 is equal to 0.3. Y sub 0 is equal to 5. So substituting that to the equations we have, starting off with k sub 1, which is k1 is equal to f of x sub 0 comma y sub 0. That will give f of 0.3 comma 5, and which is equal to 1 over 6 sine 0, the quantity 1 over 6 times the quantity of sine 0 sub 0.3 minus 10 times 5 raised to 2. That will give an answer of negative 41.6658. For k sub 2, which is equal to f of x sub 0 plus 1 half h comma y sub 0 plus 1 half k sub 1 h. Substituting, we will have f of 0.3 plus 1 half 0.2 comma 5 plus 1 half negative 41.6658. This is the value from k sub 1 times 0.2. Simplifying it further, we are gonna have f sub 0.4 comma 0.83342, which is equal to 1 over 6 times the quantity of sine 0.4 minus 10 times 0.83342 squared, and that will give an answer of negative 1.1565. For k sub 3, which is f of x sub 0 plus 1 half h comma y sub 0 plus 1 half k sub 2 h, we will have by substituting the values we will have f of 0.3 plus 1 half times 0.2 comma 5 plus 1 half times negative 1.1565 times 0.2. Simplifying it, we will have f of 0.4 comma 4.88435, and substituting it again, we will have a value of we have the equation 1 over 6 sine times the quantity of sine 0.4 minus 10 times 4.88435 square. That will give an answer of negative 39.7603. For k sub 4, which is f of x sub 0 plus h comma y sub 0 plus k sub 3h. By substituting the values, we will have f of 0.3 plus 0.2 comma 5 plus negative 397603 times 0.2. That will give f of 0.5 comma negative 295206. Solving it, we will have the equation of 1 over 6 sine 0.5 minus 10 times negative 2.95206. That will give an answer of 4.9216. Y sub 1, we have the equation of y sub 0 plus 1 over 6 k sub times the quantity of k sub 1 plus 2 k sub 2 plus 2 k sub 3 plus k sub 4 times h. So substituting the values we just solved, we have 5 plus 1 over 6 times the quantity of negative 41.6658 plus 2 times negative 1.1565 plus 2 negative 339.7603 plus 4.9216 times 0.2. That will give an answer of 1.0474. And for x sub 1, we have the equation of x sub 1 is equal to x sub 0 plus h. That will give 0.3 plus 0.2, and that will give 0.5. In continuation, we have a value of I which is equal to 1 for x sub 1, which is equal to 0.5, and y sub 1 which is equal to 1.0474. By having those values, we will again return to the original equations for k sub 1 up to k sub 4. So for k sub 1, by substituting the values, we have f of 0.5, quantity of 1.0474. That will be equal to 1 over 6 sine 0.5 minus 10 times 1.0474 squared. That will be equal to negative 1.8270. For k sub 2, we have f of x sub 1 plus 1 half h comma y sub 1 plus 1 half k1h. Substituting the values, we have f of 0.5 plus 1 half 0.2 comma 1.0474 plus 1 half negative 1.8270 times 0.2. That will be equal to f of 0.6 comma 0.8647. That will be equal, and that will be equal to 1 over 6 times the quantity of sine 0.6 minus 10 0 times 0.8647 squared. That is equal to negative 1.2444. For k sub 3, substituting the values for we will have f of 0.5 plus 1 half 0.2 comma 1.0474 plus 1 half times negative 1.2444 times 0.2. That'll be equal to f of 0.6 comma 0.923. By solving it, we will have 1 over 6 times the quantity of sine 0.6 times minus 10 0.9 times 0.923 squared. That will be equal to negative 1.4184. For case of 4, we have f of 0.5 plus 0.2 comma 1.0474 plus negative 1.4184 times 0.2. That will be equal to f of 0.7 comma 0.7638. And by solving, we will have 1 over 6 times the quantity of sine 0.7 times minus 10 times 0.7638. That'll be equal to negative 1.2710. And lastly, we will have y sub 2 is equal to y sub 1 plus 1 over 6 times the quantity of k sub 1 plus 2k sub 2 plus 2k sub 3 plus k sub 4 times h. That'll give 1.0474 plus 1.6 times the quantity of negative 1.8270 plus 2 negative 1.244 plus 2 times negative 1.4181 plus negative 1.2710 times 0.2. That'll be equal to negative 1.126 x sub 2 is equal to x sub 1 plus h, which is equal to 0.5 plus 0.2, which is equal to 0.7. So y of x sub 2 is approximately 1.1216. So y of 0.7 is equal to 1.1216.
For the fourth question, in Runge-Kutta fourth order method, the velocity of a parachutist is given as a function of time by v times t is equals to 44.2 tan h times 0.17 t. T is greater than or equal to 0. Using Runge-Kutta fourth order method with a step size of 5 seconds, the distance traveled by the body from t is equals to 2 to t is equals to 10 seconds is estimated most nearly as. For the solution, v times t is equals to 44.2 tan h times 0.17 t. T is greater than or equal to 0. The Runge-Kutta fourth order method is S sub I plus 1 is equals to S sub I plus 1 over 6 times K1 plus 2K2 plus 2K3 plus K4 times H, where K sub 1 is equals to F times T sub I, comma, S sub I. K sub 2 is equals to F times T sub I plus 1/2 times H, comma, S sub I plus 1/2 K sub 1 times H. K sub 3 is equals to F times T sub I plus 1/2 times H, comma, S sub I plus 1/2 K sub 2 times H. K sub 4 is equals to F times T sub I plus H, comma, S sub I plus K sub 3 times H. For I is equals to 0, T sub 0 is equals to 2, and S sub 0 is equals 0. K sub 1 is equals to F times T sub 0, comma, S sub 0. Substitute the values. 44.2 tan h times 0.17 times 2, K sub 1 is equals to 14.4745. K sub 2 is equals to F times T sub 0 plus 1/2 H, comma, S sub 0 plus 1/2 K sub 1 times H. Substitute the values. 2 plus 1/2 times 5, comma, 0 plus 1/2 times 14.4745, or the K sub 1 times 5. 44.2 tan h times 0.17 times 4.5 is equals to 28.4654. For the K sub 3, F times T sub 0 plus 1/2 H, comma, S sub 0 plus 1/2 K sub 2 times H. Substitute the values. 2 plus 1/2 times 5, comma, 0 plus 1/2, plus the value of K sub 2, which is 28.4654 times 5. 44.2 tan h times 0.17 times 4.5. The value of K sub 3 is 28.4654. For the K sub 4, F times T sub 0 plus H, comma, S sub 0 plus K sub 3 times H. Substitute the values. We have 2 plus 5, comma, 0 plus the value of K sub 3 times 5. 44.2 tan H times 0.17 times 7. The value of K sub 4 is equals to 36.7116. For the continuation, S sub 1 is equals to S sub 0 plus 1 over 6 times K sub 1 plus 2K sub 2 plus 2K sub 3 plus K sub 4 times H. Substitute the values. 0 plus 1 over 6 times 14.4745 plus 2 times 28.4654 plus 2 times 28.4654 plus 36.7116 times 5. The S sub 1 is equals to 157.5398. T t sub 1 is equals to t sub 0 plus h. Substitute the values 2 plus 5, the t sub 1 is equals to 7. For the next step, for I is equals to 0, t sub 1 is equals to 7, and s sub 1 is equals to 137.5398. Just repeat the steps for calculating the K1, K2, K3, and K4. But instead of using t sub 0 and s sub 0, we're going to use t sub 1 and s sub 1. For the K sub 1, f times t sub 1, s sub 1, just substitute the value 44.2 tan h times 0.17 times 7. The K sub 1 is equals to 36.7116. For the K sub 2, f times t sub 1 plus 1 half times h, s sub 1 plus 1 half times k sub 1 times h. Substitute the values 7 plus 1 half times 5 times the value of s sub 1, which is 137.5398 plus 1 half plus the value of k sub 1, which is 36.7116 times 5 is equals to 44.2 tan h times 0.17 times 9.5. For the value of k sub 2, we have 40.8362. For the K sub 3, f times t sub 1 plus 1 half times h, s sub 1 plus 1 half k sub 2 times h. Again, substitute the values 7 plus 1 half times 5, 137.5398 plus 1 half times the value of k sub 2, which is 40.8362 times 5. 44.2 tan h times 0.17 times 9.5. The value of k sub 3 is 40.8362. For the k sub 4, we have f times t sub 1 plus h, s sub 1 plus k sub 3 times h. Again, substitute the values 7 plus 5, 137.5398 for the s sub 1 plus the value of k sub 3, which is 40.8362 times h, which is 5. 44.2 tan h times 0.17 times 12. For the value of k sub 4, we have 42.7302. The formula for s sub 2 is equals to s sub 1 plus 1 over 6 times k sub 1 plus 2 k sub 2 plus 2 k sub 3 plus k sub 4 times h. Substitute the values 137.5398 plus 1 over 6 times 36.7116 plus 2 times 40.8362 plus 2 times 40.8362 plus 42.7302 times 5. For the s sub 2, we have 339.86 meters. For the t sub 2, we have t sub 1 plus h. Substitute the value 7 plus 5 is equals to 12. To get the distance traveled from t is equals to 2 to t is equals to 10, the distance traveled is equals to s sub 2 minus s sub 0. Substitute the values 339.86 meters for the s sub 2 and 0 for the s sub 0. The answer is 339.86 meters. So the distance traveled from t is equals to 2 to t is equals to 10 is 339.86 meters.
Hi, this is Mohammad, and we are going to continue to our next topic, which is parabolic partial differential equation. In this topic, we will have an answer, a questions, a problem, and there will be a multiple choice, and we will be solving for how did we get the answers and which among the multiple choice are the correct answers. Now let's proceed to number 1. For number 1, the region in which the following partial differential equation is x cubed times the second partial derivative of u with respect to partial derivative of x squared plus 18 times the second partial derivative of u with respect to partial derivative of y squared plus 2 times the second partial derivative of u with respect to partial derivative of x and partial derivative of y plus 5u is equals to 0. This equation acts as parabolic equation when A, x is less than 1/18 raised to 1/3, B, x is equals to 1/18 raised to 1/3, or C, x is greater than 1/18 raised to 1/3, or D, for all values of x. Now, among all of this question, which is correct? Try to solve it. And the correct answer is B. How? We will show you how we solve for it. The correct answer is letter B, because a general partial differential equation with two independent variables is of the form of A with second partial derivative of u with respect to partial derivative of x squared plus B times second partial derivative of u all over partial derivative of x and y plus C second partial derivative of u all over partial derivative of y squared plus D is equals to 0, where A, B, and C are functions of x and y, and is a function of x, y, u, and partial derivative of u all over partial derivative of x, and partial derivative of u with respect to partial derivative of y. So for the question above, to be parabolic, we use the equation b squared minus 4ac is equals to 0. So in the question above, they have given us a is equals to x cubed, b is equals to 2, c is equals to 18, giving b squared minus 4ac is equals to 0. Now we get, and solve for it, we get x cubed is equals to 4/72. And solve for x, we get x is equals to 1/18 raised to 1/3, which is, on the problem, on the multiple choice, is letter B, which is x is equals to 1/18 raised to 1/3.
In question number 2 in parabolic PDE, the question is the partial differential equation of temperature in a long thin rod is given by partial derivative capital T over by partial derivative of small t is equals to alpha partial derivative squared T capital divided by partial derivative of x squared, and the figure is given there. If alpha is equals to 0.9 centimeters squared per second, the initial temperature of rod is 45 degrees Celsius, and the rod is divided into 3 segments. The temperature at node 1 using delta T is equals to 0.1 second by using an explicit solution at T is equals to 0.3 second is letter A 46.0175 degrees Celsius, B 46.7015 degrees Celsius, and C 45.1075 degrees Celsius, and D 45.5701 degrees Celsius. So solution, given that alpha is equals to 0.9 centimeters squared per second, and delta T is equal to 0.1 second, and T is equals to 0.2 second, and L is equals to 9 centimeter second, and N is equals to 3. Delta X is equals to L over N. So we're going to substitute, is equals to 9/3, therefore delta X is equals to 3. So the number of times step is equals to T final minus T initial divided by delta T. So we're going to substitute 0.2 minus 0 divided by 0.1 is equals to 2. So lambda is equals to alpha delta T divided by delta X squared is equals to lambda is equals to 0.9. Substitute the 0.1 divided by 3 is equals to 0.01. So the boundary condition of all j is equals to 0.1 for all t raised to j sub 0 is equals to 80 degrees Celsius, and t raised to j sub 3 is equals to 20 degrees Celsius. The initial temperature of the rod is 45 degrees Celsius. That is all the temperature of the nodes inside the rod are at 45 degrees Celsius when time t is equals to 0 second, except for the boundary nodes. This could be represented as t raised to 0 sub I is equals to 20 degrees Celsius for all I is equals to 1, 2. Solution. The initial temperature at the nodes inside the rod when t is equals to 0 second. T raised to 0 sub 0 is equals to 80 degrees Celsius. T raised to 0 sub 1 is equals to 45 degrees Celsius. T raised to 0 sub 2 is equals to 45 degrees Celsius. And T raised to 0 sub 3 is equals to 80 degrees Celsius. So, temperature at nodes inside the rod when T is equals to 0.1 second, setting J is equals to 0 and I is equals to 0, 1, 2, 3 gives the temperature of the nodes inside the rod when time is T is equals to 0.1 second. T raised to 1 sub 0 is equals to 80 degrees Celsius boundary condition. T raised to 1 sub 1 is equals to T raised to 0 sub 2 plus lambda multiplied by T raised to 0 sub 2 minus 2 T raised to 0 sub 1 plus T raised to 0 sub 0. So, it equals to 45 plus 0.1 multiplied by 45 minus 2 multiplied by 45 plus 80 is equals to 45.35 degrees Celsius. So, temperature at nodes inside the rod when T is equals to 0.1 second. T raised to 1 sub 2 is equals to T raised to 0 sub 2 plus lambda times T sub 3 raised to 0 minus 2T sub 2 raised to 0 plus T sub 1 raised to 0 is equals to 45 plus 0.1 multiplied by 20 minus 2 multiplied by 45 plus 45 is equals to 45 plus negative 0.25 is equals to 44.75 degrees Celsius. T raised to 1 sub 3 is equals to 20 degrees Celsius boundary condition. So, temperature at nodes inside the rod when T is equals to 0.2 second, setting J is equals to 1 and I 0, 1, 2, 3 gives the temperature of the nuts inside the rod when time is T is equals to 0.2 second. 2 sub 1 raised to 2 is equals to 80 degrees Celsius boundary condition. T raised to 2 sub 1 is equals to T raised to 1 sub 1 plus lambda multiplied by T sub 2 raised to 1 minus 2 T raised to 1 sub 1 plus T raised to 1 sub 0 is equals to 45.35 plus 0.01 multiply quantity 44.75 minus 2 times 45.35 plus 80 equals 45.35 plus 0.6675 is equals to 46.0175 degrees Celsius. So, we're going back to the given multiple choice. So, the correct answer is letter A, which is A is equals to 46.0175 degrees Celsius.
For question number 3 of parabolic PDE, the region in which partial differential equation x squared partial squared u over partial x squared minus 8 partial squared u over partial x partial y plus 64 partial squared u over partial y squared plus 2u equals 0 acts as parabolic equation has been asked. In answering this, we need to evaluate the equation first. So as shown in the slide, we can say that this equation consists of two independent variables where a, b, and c are functions of x and y and is a function of x, y, u, and partial u over partial x and partial u over partial y. To make this equation parabolic, we will be using formula b squared minus 4ac equals 0, where a is equal to x cubed, b is equal to negative 8, and c equals to 64. Substituting this value to the given formula, we acquired 64 over 256 as the value of x squared, thus x is equal to 1/2.
So for the fourth question for the parabolic PDE, we have: consider steel rod that is subjected to a temperature of 160 degrees Celsius on the left end and 40 degrees Celsius on the right end. If the rod is of length of 0.1 meters, use the explicit method to find the temperature distribution in the rod from t is equal to 0 and t is equal to 6 seconds. Use delta x is equal to 0.02 meters and 0.02 meters, and delta t is equal to 2 seconds, and the initial temperature of the rod is 20 degrees Celsius. So for listing the given, we have for K 54 watts per meter Kelvin. For P, we have 7,800 kilogram per cubic meters. For C, we have 490 joules per kilogram Kelvin. So for the solution, since the explicit method is written as T sub I raised to j plus 1 is equal to T sub I raised to j plus lambda, the quantity of T sub I plus 1 raised to j minus 2 T sub I raised to j plus T sub I minus 1 raised to j. So we try to solve first for the value of lambda, which is equal to alpha delta t over delta x square is equal to k over pc, quantity of delta t over delta x square. So instead of substituting the values, we will have 54 over the quantity of 54 over 7,800 times 490 times the quantity of 2 over 0.02 square. That will give 0.0706, and thus we will have t sub I raised to j plus 1 is equal to t sub I raised to j plus 0.0706 times the quantity of t sub I plus 1 raised to j minus 2 t sub I raised to j plus t sub I minus 1 raised to j. For the temperatures, j is equal to 1 comma t is equal to 2 seconds, and we will set j as is equal to 0. So we have this stable value here from t sub 0 raised to 0 to t sub 5 raised to 0. We have range of values from 160 degrees Celsius, 20 degrees Celsius, 20 degrees Celsius, 20 degrees Celsius, 20 degrees Celsius, and 40 degrees Celsius. For I is equal to 0, we have t sub 0 raised to 1, which is equal to 160 degrees Celsius, which is the boundary condition. For I is equal to 1, we have t sub 1 raised to 1, which is equal to t sub 1 raised to 0 plus lambda times the quantity of t sub 2 raised to 0 minus t sub 1 raised to 0 plus t sub 0 raised to 0 is equal to 20 plus 0.0706 times the quantity of 20 minus 2 times 20 plus 160, which is equal to 29.88 degrees Celsius. For t sub 2 raised to 1, it is equal to t sub 2 raised to 0 plus lambda has the quantity of t sub 3 raised to 0 minus t 2t sub 2 raised to 0 plus t sub 1 raised to 0. By substituting the values we will have 20 plus 0.0706 times the quantity of 20 minus 2 times 20 plus 20, and that will give 20. For t sub 3 raised to 1, we will have it is equal to t sub 3 raised to 0 plus lambda has the quantity of t sub 4 raised to 0 minus 2 t sub 3 raised to 0 plus t sub 2 raised to 0. By substituting the values we have 20 plus 0.0706 has a quantity of 20 minus 2 times 20 plus 20, and that will also give 20. For t sub 4 raised to 1, that will be equal to t sub 4 raised to 0 plus lambda has a quantity of t sub 5 raised to 0 minus 2 t sub 4 raised to 0 plus t sub 3 raised to 0. By substituting, we have 20 plus 0.0706 times the quantity of 40 minus 2 20 times 20 plus 20. That will give 21.412. For t sub 5 raised to 1, we have 40 degrees Celsius, which is the boundary condition. So in gathering all the values we have, we will get this temperature distribution for t at 2 seconds. So for the temperatures, J is equal to 2 minus J is equal to 2, comma T is equal to 4 seconds. We will set J is equal to 1. For I is equal to 0, T sub 0 raised to 2 is equal to 160 degrees Celsius, which is again our boundary condition. For I is equal to 1, we have T sub 1 raised to 2 is equal to t sub 1 raised to 1 plus lambda times the quantity of t sub 2 raised to 1 minus t 2t sub 1 raised to 1 plus t sub 0 raised to 1. Substituting, we will have 29.88 plus 0.0706 times the quantity of 20 plus minus 2 times 29.88 plus 160, and that will give 38.37 degrees Celsius. For t sub 2 raised to 2, it is equal to t sub 2 raised to 1 plus lambda times the quantity of t sub 3 raised to 1 minus 2 t sub 1 raised to sub 2 raised to 1 plus t sub 1 raised to 1. Substituting, we have 20 plus 0.0706 times the quantity of 20 plus minus 2 times 20 plus 29.88, and that will give 20.70. And for t sub 3 raised to 2, we have it is equal to t sub 3 raised to 1 plus lambda times the quantity of t sub 4 raised to 1 minus 2 t sub 3 raised to 1 plus t sub 2 raised to 1, and that will equal to 20 plus 0.0706 times the quantity of 21.412 minus 2 times 20 plus 20, and that will give 20.10. For t sub 4 raised to 2, we have it is equal to t t sub 4 raised to 1 plus lambda times the quantity of t sub 5 raised to 1 minus 2t sub 4 raised to 1 plus t sub 3 raised to 1. And that will give 21.412 plus 0.0760706 as the quantity of 40 minus 2 times 21.412 plus 20, and that will give 22.62. And lastly, for t sub 5 raised to 2, we have 40 degrees Celsius, which is again the boundary condition. So gathering all those values, again we will make a table of values for t is equal to 4 seconds, and that will be our temperature distribution. And so at temperatures at J is equal to 3, comma T is equal to 6 seconds, we will set J is equal to 2. For I is equal to 0, T sub 0 raised to 3 is equal to 160 degrees Celsius, which is again our boundary condition. For I is equal to 1, we have T sub 1 raised to 3, which is equal to T sub 1 raised to 2 plus lambda times the quantity of T sub 2 raised to 2 minus 2t sub 1 raised to 2 plus t sub 0 raised to 2. And by substituting, we will get 38.37 plus 0.0706 times the quantity of 20.70 minus 2 times 38.37 plus 160, which is equal to 45.71 degrees Celsius. For t sub 2 raised to 3, that'll be equal to t sub 2 raised to 2 plus lambda times the quantity of t sub 3 raised to 2 minus 2 t sub 2 raised to 2 plus t sub 1 raised to 2, and that will be equal to 20.70 plus 0.0706 times the quantity of 20.10 minus 2 times 20.70 plus 38.37 is equal to 21.91. For t sub 3 raised to 3, it is equal to t sub 3 raised to 2 plus lambda quantity of t sub 4 raised to 2 minus 2t sub 3 raised to 2 plus t sub 2 raised to 2. Substituting, we have 20.10 plus 0.0706 times the quantity of 22.62 minus 20.10 plus 20.70, and that will give 20.32. For t sub 4 raised to 3, it is equal to t sub 4 raised to 2 plus lambda times the quantity of t sub 5 raised to 2 minus 2t sub 4 raised to 2 plus t sub 3 raised to 2 is equal to 22.62 plus 0.0706 times the quantity of 40 minus 2 times 22.62 plus 20.10, and that is equal to 23.67. And lastly, for t sub 5 raised to 3, we have it for 40 degrees Celsius, which is again boundary condition. And for the last temperature distribution of values, we gather all those values for t is equal to 6 seconds. And this is now our table of values.